Yes, so please, Matteo.
Okay. So I was saying, thank you for inviting me. And as the professor was saying, this is an application of the use of networks that is kind of new, actually. We started this project 1 year and a half ago to study, it says the presentation, the state of the space resident population. So I will go over what all of this means and how we do it and etc. But basically, why space? Why space? Because actually, space is the last environment that we have polluted as humanity. So we use space related services every day, like satellites, GPS, communications, and everything. However, all of these comes at a cost, the cost of crowding space with a lot of objects. Some of them are active, so all the satellites that we use. Some of them instead are not active. So most of them actually are debris, or better, defunct objects, dead satellites, fragments of satellites that have exploded or collided, fragments of rocket bodies that have been left in orbit after carrying the satellites in space. And actually, we can count them in numbers actually quite high. I will see. You will see. And more or less, the trend has been to steadily increase the number of launches. We have seen an explosion in the last decade. We have seen an explosion of the number of fragmentation debris because of explosions. Sorry for the pun. And now, in the last few years, there are projects, either future or already ongoing, to further increase our utilization of space and the number of objects that orbit the Earth by creating mega constellations. So constellations of satellites of hundreds or even thousands of members. So this has become quite the complex system that you study. And in particular, it has become complex in the sense that all of these objects, while they don't interact gravitationally, so directly between each other, all of their orbits, all of their dynamics and movement is uncoupled from the others. However, they encounter each other, they pass near each other, and so there is a risk of collision. There is the risk of destruction of existing satellites. There is the risk of producing more fragments that may damage other satellites, other bodies, and produce fragments, and going on like this. And so this has become very important to prevent this and to study risk of collision in space. What we do, in fact, is to use networks. We go over, we collect data about the space resident population. There are several catalogs that are up to date each day by several maintainers, similar entities that maintain these catalogs. We obtain data about their state, so their position in space, their uncertainty that is related to this position in state. And then we combine them in order to obtain a representation via a network. This network is then studied to show the interaction between the objects, to highlight several properties that we then use to create some kind of measures of scores that measure risk or sustainability of all of the population. So after this introduction, I will go over a bit of nomenclature on space, on the space population. and how we go from space objects to networks. So there are several steps. I will go over them. I will then introduce some of the aspects of networks that we study in this project, showing you how the network embedding is then used to create some metrics, how it is used actually in order to create some metrics, and these metrics are used to study real life situations. So, as I was saying, the space resident population is composed of more than 30,000 objects that we can track, and so track via, for example, telescopes or radio telescopes that we can, of which we can compute the trajectory, and of which we can catalog. Most of them are actually debris. Only a fraction of them are active satellites up to date. Debris are what is called normally space junk, so some artificial objects that are uncontrollable, whether it is the whole satellite after it has finished the fuel that it needs to operate, or if it's a small piece of a few centimeters long. The main problem with this situation is that we can only detect objects that are large enough to be seen by telescopes on the ground. So around 10 centimeters. All of the smaller ones can only be estimated, and they are in the millions in the number of millions. And as I was saying, the dynamics of these objects is completely uncoupled. So we don't use networks to describe the dynamics, the coupled dynamics of these objects, because they are too small to interact gravitationally between each other. But what we do is to represent the interactions between them. So conjunction, what we call conjunctions. And we study these objects, at least in our project, by, for example, obtaining from a database the description of the state of these objects. There are, for example, what we see here, TLEs, two-line elements, that are a very compact way to represent the state of an object at a given time, that contains the most important parameters to describe its orbit, to identify it in space, and to describe how the orbit is changing in time, so we can compute the position in the future. There are main actually regions of space where these objects are concentrated. These are the most, let's say, the most important families of orbits. We have the low Earth orbit, LEO, here. It is below 1,000 to 2,000 kilometers, so very close to the atmosphere. We have, which is also used for, which is mainly used for communication and imaging satellites. We have medium Earth orbit, so MEO, which is much higher and is used mostly for navigation satellites like GPS, for example. We have the geostationary orbit, which is at a precise height in order to obtain a revolution period around the Earth that is the same time as the rotation period of the Earth, so that a satellite can always be above the same point of the Earth, for example, for climate observation. And we have geostationary transfer orbit, which are, as the name implies, is the orbits that are used to transfer to the geo orbit. And so different satellites, different orbits, and different families of the population, within the population, that are focused here. And we can see actually that most of them are concentrated in the low Earth orbit, which is by far the most crowded, with most of the active communication satellites, imaging satellites, and also most of the defunct ones and most of the debris that have been produced by previous fragmentations, previous collisions, one of them accidental, some of them intentional. So we have this, you can see object count is in the order of 15,000 in Leo now, and about in general, well above 20,000, almost 30,000. Just a very quick I will use the term orbit propagation, which simply means the integration of the equation of motions that describe the orbit of a satellite or an object in space from its initial state to the final state. We have various propagators, so we have various ways to compute them. I won't go over this. Here instead, it's how we, for example, once we have propagated the orbits of the satellites, so we have their trajectory in time, how we determine whether there is a conjunction, meaning whether there is an encounter between these satellites. There is, instead of comparing each couple of objects, which would actually mean a lot of comparisons. So if you consider, for example, 30,000 objects, 30,000 squared, it's a lot. For example, for a period of time that is the next few days, it becomes quite expensive computationally. So we have these series of filters that, for example, reduce the number of comparisons that we have to do. For example, by first considering the geometry of the orbits, so the relative geometry, whether it allows for an intersection for a close encounter. Then we look at the actual distance between the orbits, if they can intersect, to determine if the intersection is below a given distance that we agree on. And then the final filter actually looks at the distance between the objects. So if we determine that a conjunction is possible at some point in time, then we go and check whether this conjunction actually happens. So we consider the positions of the objects at each time, at each epoch, and we check whether, for example, they are below 1 or 3 kilometers within each other, and we consider that a conjunction. And I have said about conjunctions earlier, I have said about objects that there are uncertainties. All of the determination of the state of the objects, so their position and velocity in space, is done mostly by observations from ground and partially also from the data that the satellites collect about themselves, about their surroundings, and transmit to the ground. Which means that we have a series of uncertainties that we have to consider in our model. Some of them are actually related to the object or to the model, but what we use for example, for the estimation of the probability of collision is to use only the uncertainties over the position of the object. And these are, since due to the way it is computed, it is always represented as a Gaussian distribution in 6-dimensional, 3 dimensions of space, 3 of velocity. And so there is a covariance matrix that is used. It is associated with each orbital state, a 6x6 matrix. And this represents an ellipsoid, so some kind of ellipsoid around the nominal position of the satellite that represents where it is most likely to find it. And we use this information in order to compute during a conjunction the probability of a collision. So we consider the ellipsoids of uncertainty and we compute the probability of collision. We obtain a number, And usually, if that probability is high enough, there are a series of procedures that are activated in order to observe even more the two satellites that are involved in the possible collision, recompute the probability, and eventually perform a maneuver to send instructions to a satellite in order to change its orbit and avoid the collision. Saying all of this, that should give you a complex context of what is the situation, and also of why we do this and how we do this. And so we have seen that we have the means to go from states objects to space objects to obtain a representation of their state, of their trajectory, to determine whether they encounter each other. So if they have an interaction, quotation marks. And so we have now a ways to create a network out of these interactions. So we can, for example, the way we do this in our work, we have two ways. One is the slow way. So from the database to obtain the orbital states, propagating, filtering, and creating these, eventually also computing probabilities and obtaining this network embedding. So nodes, links, and weights of the links. And there is a faster weight, which is, however, less flexible, which uses what we see here is written as CDM, so conjunction data messages. These are actually notifications that some entities give to release publicly or give to satellite operators to notify them that there will be a conjunctions with a risk of collision, and they do all the previous work for us, because they already include all the conjunctions with probabilities, epochs, which are the satellites, and so on. And actually, I can show you what we obtain from this. I will give you, this is a lot. So for example, using conjunction data messages that have been combined from May 1st to the 31st of May. So for the whole month of May, we obtain something similar. So we have a network that is actually, I will show details of the network. This network, of course, I just wanted to show you the full picture. So we have a network that is actually composed of several components, separate components, all of them of various shapes, various sizes, with different objects within them. So the separation of these components depends on various parameters. So for example, CDMs, as I was saying earlier, they are less flexible because they are always use propagations of 3 days. So they check for conjunctions only 3 days in the future. And they consider conjunctions encounters between objects below 1 kilometer. So this is actually quite restrictive, and it's practical. It's what is mostly used for safety measures. But if you want to build a big network, it's quite constricting, because you rely on short-range interactions, and so you obtain all these various components that depend, for example, on the position of the objects. So mostly on the families of objects in our population, whether their orbits are close enough to allow for a conjunction, the time period. So these conjunctions can happen in 3 days or can happen in 4 days, which means they won't be seen, let's say. And so we have different components. If we exclude, of course, all the isolated nodes, we have in here for this kind of simulation more than 1,300 components with actual size actually very small, because these actually suggest that most of them are just couples in two satellite interactions that they simply encounter each other and no one else. However, this picture considers only the components with with more than 5 nodes for simply to make it less confusing to see, to look at. In this case, you can see that the average size is actually larger. However, the maximum size is actually 200 nodes, and we can actually see here there are here I'm showing you the two largest components of this network here. The largest one is made of 200 nodes, the second one of 125. And what I did was to map the collision probability as the weight of the edges of these nodes. So this is actually a nice way to represent, a very compact way to represent this kind of interactions between objects, so the conjunctions, the close encounters. Since you can also map the collision probability over the link that represents the conjunction. And so you can immediately see that there are a couple here of conjunctions that are quite high in probability. Unfortunately, it's not very easy to make visible, since smaller probabilities mean a dark color and a very thin edge. However, you can, I will share the presentation, and however, you can see here there are various there are already various informations that we can extract from this just by looking at this. And instead, I wanted also to show you the other way, the other results. So now if we look at the propagation, so we actually have to integrate the equations of motions of the satellites, of all of these objects over 30 days. We consider in this case 3 kilometers as conjunction limit, just to make it, let's say, make the components larger, and for reasons that you will see later. And we get a similar situation. We have 1,000 components initially, with mostly actually very small components that are made of 2 or 3 satellites that only encounter each other and no one else, because space, however, it's big. And so most of these objects actually, there are some objects in some orbits that are actually pretty isolated. However, if we consider, for example, here, the largest 2 components, we see that the large one is 447 nodes. The second one is around 40 nodes. And again, we can map the collision probability here and see how these interactions are relate to the risk of a collision. So I wanted to show you these results just to see that there are different ways, different initial data that we use to obtain the network, and this reflects actually on the shape, on the topology of the network. So they have different shapes, different components, but as I said, they are always composed of several components that are separated from each other. And we can actually say in both cases, we can actually comment also on the shape of these components. They have usually different shapes, but you can see they are very branch-like. So this is due to the fact that, as I said, satellites mostly encounter, each satellite mostly encounter very few other satellites in orbit. However, over long time, it will one satellite, one object will encounter one, and then will encounter another, and then will encounter another, and so all these little bridges are formed that connect several families of satellites that maybe interact more often among each other. Actually, I can actually show you here. So we have just looking at this picture. So the largest component here. What happens? So this has been obtained by considering, for example, by considering an initial condition on the 1st of May, and then the trajectory over the next month for each object. However, we can actually see what happens if we consider, for example, only one day. I forgot to write down the values, but for example, this is one day. We obtain only very few interactions, and this is actually what happens if we consider only one day in the future. We have very few two object interactions. They simply encounter one satellite, one other object, and that's it for the day. However, if we increase the amount of time, so 3 days, so 1 day, 3 days, 5 days, 7, 10, 15 days, 25, and then 30. No, this one was 30. We can see that as we wait, we see these all separate components. I try to keep the same layout of the previous picture, just to show you how this network grows as we, for example, keep going ahead in the future, keep going forward in the future, as there is a conjunction, and then an object has a conjunction with another object and makes a bridge between two separate components. And we can do the same actually with the distance. If we consider, for example, only 1 kilometer, we have again a lot of separate couples. If we then consider 3 kilometers, 2 kilometers, we have larger groups, as as with they have more possibility to interact with each other. And then if we consider the whole 3 kilometers, then we see that again there are some bridges forming around the various components. And so this was just by. So now I have explained to you how we go from space, objects in space, to networks, and what are the main characteristics of these networks, how they are, they reflect the actual, for example, the actual dynamics of the objects, the actual relative or geometry of the various orbits in space, the various families, and so on. And now I will go over how we study these networks in order to actually do something with them. So as I said, we have these networks whose nodes represent cataloged space objects, whether they are satellite or fragments or debris. And then we have a link, an edge between each node, between each two nodes that represents a close encounter between them. And I mentioned this before. We weight this link, so we assign a number to them that is equal to the probability of a collision between the two objects. However, there are several properties. You have seen them. The professor told me. that you can extract from the network, from the topology of the network, from the matrix of adjacency, and so on. But I want to focus more, mostly on these four that you see here, because they actually are related to various, let's say, real physical aspects of this problem. For example, the degree of a node is the number of links, the number of edges that are connected to the node, which represents the number of encounters that this object that is represented by the node has in our time span. So the higher the degree, the higher the number of conjunction, and the higher the risk of collision with something else. The clustering coefficient, so it represents the density of links around the node. So how dense is the neighborhood of a given node. And so we can identify the groups of objects in space that, for example, will be affected if there is a fragmentation, if there is a collision, if there is a cloud of fragments that is produced that will actually affect many other satellites, many more objects than the ones that are simply connected to, for example, to the central node here. And then we have other centrality measures, in particular closeness and betweenness. Closeness is related to the mean shortest path distance that connects a node with the rest of the network. And betweenness actually represents the number of shortest paths that pass through a node. Why are these important? Well, you have to consider that during a collision, there are fragments, there are debris fragments that are produced. And these fragments then may go on and hit another object, and if large enough, produce a high number of new debris, which then again can hit other objects. Consider that the relative speeds usually in low Earth orbit, the orbital speed of an object in low Earth orbit is around 7 kilometers per second, and the average collision speed is around 11 kilometers per second. So there is a lot of energy attached to each object, even small. And so even a small object can collide with another one and produce a lot more debris that can hit other objects. And so these two measures can be related to chains of collisions that may happen in orbit. So chains of collisions between debris of debris of debris. And so we can actually study these four, for example, are the ones that we chose to focus on, these four properties. For example, in our network, we can see the degree. We can identify the objects. So we know that the maximum degree is 2. The mean degree is actually around 2, but as I said, it's because it has this kind of branching structure. So with a lot of chains attached to a few nodes that act as hubs. So we identify the objects that have the highest degree, so which have the highest probability of colliding with another one. But then we can measure the closeness, for example. And so to identify dense neighborhoods of objects, which is, you can see that central part. And so these are actually will be the ones that are at risk of encountering a debris cloud, where if one of them will have a fragment. And then we can also visualize betweenness. So we can show which are the objects that have the highest probability of propagating a debris cloud when they are hit by another object. And so we can combine, we can look at these all these properties and already have an idea of how to interpret them in a real physical way that is related to the risk of collisions. But then we can also combine them. I will show you how. And this one is simply to show you what happens if we increase the distance limit for the conjunctions to 5 kilometers. So from 3 to 5, then the largest components go. The largest component goes from, sorry, I don't remember, around 400 something nodes to 4,000. And while the second one is around 1,000, you can see there are still these branches, these chains that extend. However, there is now a central cluster of very highly interconnected nodes, and this is why we increase. This is why we. This is due to the fact that we have increased the distance. So, as we increase even more, then we can connect to even more groups. So you see, for example, in this picture of the largest component, there are several branches, chains, but now there are bridges between the chains, because even while below 5 kilometers, with less than 5 kilometers, they are separate. If we extend our detection distance further and further, then there will be connection, more and more connections. And if we take this to the limit, to the extreme, by having infinite distance, we will have the whole population connected, whole population in a fully connected network. This is just to add more to the explanation of how our parameters and how the physical world reflect into the network. And so now I said we have studied, we have selected a few properties. We have a way to study them. Now we can actually use them to we can actually combine them in order to obtain informations about, for example, the risk of collisions. As I said, we have different measures. And let's say now that we only want to consider the topology of the network. We don't consider that we ignore the fact that there are different kind of objects. There are the conjunctions happen at different times. We actually ignore even the actual probability of collision itself. We will use simply a p value equal for everybody, for all the conjunctions, that it will help us to combine the various informations. So now, for example, if we consider that all these objects, all these events, all the conjunctions are mutually exclusive, which is not true in reality, but we use this as an approximation. So we can start, for example, from the degree. The degree is the interactions between the neighbors. So it depends on the number of neighbors. If, for example, with this node A here that is highlighted, we want to compute the probability of a collision. We know that these collisions are mutually exclusive. Then we go and we can sum the probabilities, and what we obtain is the sum of the probabilities, which actually highlights the presence of the degree. So we have a first contribution here that is directly related to the degree of the object of the node, simply by combining the probability of collisions, the probabilities of collision of this object with other objects. Now, if we want to consider, for example, not the local effects, but the indirect collisions, we can, for example, study, for example, estimate the probability of a collision of A, not with one of its neighbors, but with the debris produced by one of its neighbors. So one of the neighbors of A collide with another object, produces debris, and which then goes and hit A. If we combine these probabilities, trying to compute the overall probability, we have something that depends on the number of links between the neighbors of A. So the number of triangles that connect to A, which actually relates to the clustering coefficient. And we can actually reorganize the expression in order to obtain, to, let's say, literally highlight the presence of this coefficient in the expression. And then we go on and consider even more distant interactions. So we go and, for example, what if something produces debris that then hits another object, which produces another debris that hits another object, and so on. What is the risk for A? What is the probability that A is hit by an object that is produced in such chains? Well, if this is the product of probabilities over all the chains that connect to A, so it is related to the length of these chains. So to the length, to the length of the paths that from A to other nodes, that go from A to other nodes, which means they can be related to the centrality measures that I showed before to the closeness, for example. And so we have a measure, we have a way to compute the average path length from A. Then we sum all of these, and actually we can include also the betweenness. The betweenness represents the number of shortest paths that pass through a node. And so we can say that A, we can represent this way. One, the probability that A is hit by a debris in this node, in one of these nodes, and also the probability that A contributes itself in the chain by furthering it, by propagating it further with new debris that then will go on to hit other objects. And so we can sum all these contributions that actually highlight the various properties of the same network that we were studying. Here I just made a simple simplification to obtain something more, let's say, more elegant, more nice to look at. But here we have an expression that combines the properties that can be obtained by looking simply at the topology of the network, and actually represents some sort of probability of collisions, direct or indirect, inside the network. And we can, for example, represent this. And we see that we can identify the highest, for example, the top five objects with the highest score. And we see that more or less, let me see here. So we had seen that this object was the one with the largest degree. These objects here, this neighborhood was the one with the highest closeness, and this group here was the one with the highest betweenness. And more or less is what we see here. We see these objects pop out, pops up from the other one, from its neighbors. This group here, this central group, actually has a higher score because it has strong, many connections with the various objects, and all these objects can actually bridge various fragmentations, so they can propagate chains of fragmentation. So all of these aspects can be summed up into a score, and we can identify this by looking at this. It actually has more or less what we were expecting by looking separately at the three properties. While the rest, you see more or less the rest of the, apart from a few objects, the rest of the network has low score because they are mostly chains separate from the central part of the network. And so they don't contribute much to the probability of collision overall. And now we want to go further. We consider now, we remove some assumptions. We consider a different kind of objects. Now I want to go over this as in detail. In this case, I want to simply highlight that we don't use anymore the properties themselves. So we don't use the actual coefficients, the expression of the degree or the clustering and so on. But instead, we still combine the probabilities by, in this case, making a distinction between say, smaller, larger objects. And we use the network as a guide to combine the probabilities, not anymore using directly the information of the topology, but using it as a guide. Again, the contributions are still related to the same aspects. So we have the potential to hit other objects, to be hit by others, the potential to encounter a debris cloud, the potential for chains of fragmentations to propagate. These are still related to the properties that we have seen, that we have selected as interesting, as related to physical, to real aspects of our dynamics. But they are not them anymore. They are just a guide. And so we can now represent again this ranking score, this ranking. And you see actually here, well, it considers now the actual probability of collision. So there are different objects that are top ranking. However, there is still the same object as before, this central object here, which means that it has actually the same ID, yes, which actually means that these two scores, these two ways to combine the information of the network are agree with each other, which means they have some sense to it. And now,
Matteo?
see?
Sorry. So, can you go over what is the main difference between the two scores? So before you went
Yes.
directly all this betweenness. So now what have you in the second?
Yes. So in this case, in this score, what I wanted to do was to actually have actually show these parameters here, these coefficients directly in the expression. So I wanted these coefficients, and they actually come out of the expression if you consider simply by considering the links as probabilities of collisions and combining them. So this is only based on the topology of the network.
Yeah.
There is no other assumption. I mean, there are a lot of assumptions, but there is no other, let's say, relevant aspect.
Yes.
In the second one, instead, I remove some of the assumptions. I consider, for example, that the probabilities are actually have a value from different from each other. So there is the actual collision probability here represented. There is now a distinction between small and large objects because they have different different energy. They produce different number of debris, and so they have different, say, they are different kinds of threat for the other objects.
And this
and
is
so,
expressed, and this is expressed in this expression. This is like
yeah, sorry.
psi, or will be this?
Yes, no, yeah, this psi parameter. Sorry, this psi parameter is the distinction between the objects. It's 1 or 0 for small and large.
Okay, thank you.
But the thing is that now that the probabilities have all different values, if you sum them up like before, you don't obtain the degree anymore, because you don't obtain, for example, in this case, 1, 2, 3, 4, 6 times p in this case, because they are 6 different values of probabilities. And so even if the coefficients don't appear anymore directly, it's the meaning behind them that is used to guide the definition of this score. Was
Yeah.
I clear?
Yes, yes, yes. Thank you. That's very
Yeah,
clear.
okay. Okay. And now I wanted to show you actually what we do with this score. Okay, we can identify objects that have a high risk of collision, but we can actually go even further. So as an application, we can check, for example, the relative values of these scores, of the scores of different objects. We can check, for example, we can evaluate the evolution of these scores of this score in time, or for example, following a fragmentation, following the addition of a new object in the network. And for example, by considering these measures, define some categories that say this is a good performance, this is a bad performance. Performance meaning, for example, this is an increase of the risk, a decrease of the risk of collision. This is good for sustainability or not. In this case, X and Y are, for example, any two objects. For example, the current value against the new value in 1 week, or after the addition of a new satellite to orbit, or the ranking of an object, or better, the score of an object compared with the average score of the population, and so on. And I want to show you, want to do it by showing you an example. So an actual example. So this happened in 2009. This is the only accidental collision between two satellites that have ever been recorded, ever occurred. So these two satellites, Iridium 33 and Cosmos 2251, were one Russian and one American satellites, communication satellites, and they collided with each other. There have been other other collisions in orbit in history. However, they were all intentional. They were all ballistic tests. So satellites shot down with missiles in order to test defense systems and so on. So this is the only one that has actually happened by accident. And so these two satellites collided and produced thousands and thousands and thousands of debris that are still up there to this day. So after 24 years, they are still there. And I wanted to show you actually what happens, for example.
How big the satellite to produce all this debris?
Size, its size was maybe a few meters. Imagine a big truck. As weight, usually they are around 1 ton. Well, this was actually before. Now there are, with lighter materials and more efficient, let's say, engines, you can have lighter structures, carry around less fuel, and so you have lighter objects, lighter satellites. But usually, now the thing is that I didn't write the full, say, the exact numbers, but yeah, it's been, each of them produced a debris cloud of a few thousands detectable objects. So detectable meaning larger than 10 centimeters. most of them decayed in the atmosphere, so were slowed down by the atmosphere, the residual atmosphere that there is at very high altitudes over time, and fell down into the atmosphere, so fell down on Earth. But a good number of them are still in orbit. A very large number of smaller objects that have never been detected, but have been estimated. So yeah, as I was saying now, so for example, this is the propagation of these are the networks that are being obtained by propagating the networks, the initial conditions. I think it was for a few days with 1 kilometer distance. This was 1 kilometer distance. And you see that there were already there were in the first place, fewer objects in orbit. So conjunctions were less common. They still happen, but were less common. So you can actually see it here reflected on the 1st of January. So 1 month before the collision, you see just couples of objects encountering each other with very little collision probability. If we instead look at the state almost 2 months after, we can see that the situation has changed dramatically. The collision probability is higher. There are more and more, simply 2 months after, there are way more conjunctions, where way more components. The components are larger, and collision probability is higher. The ranking score is higher, and we can actually represent. However, what is nice is to consider what would have been without the fragmentation. So if we remove the fragments from the collision, we are back to the same situation as before. There are a few more because there are a few more components, because there have been a few launches in the meantime, but the networks are still simple. The probability of collision and the ranking is very low. And so it's nice to see, to study, for example, what would have been and what was and what would have been with and without a collision. So we can, for example, the probability of having at least one collision in time. We can see that there is a clear difference between before and after. There is almost 3 times as likely to experience a collision in orbit, and there is a clear difference between the 2 scenarios, with or without the collision. And for example, we can study how this probability changes and how the ranking changes. For example, we see that there is a spike after the event for both. And we can use these categories that we have created earlier by considering the scores that we have created by combining the properties and the topology of the network with the probability of collisions. And we can, for example, identify whether these events have been good or bad. In this case, they have been bad. There was no need to compute a score and assign a category, but we can actually quantify it and address and say attach a meaning to it. So this one was, say, an application of all that we have seen. We can go from conclusion. So we can go from objects in space that have gone their orbits and actually and don't affect each other, but simply pass close to each other with a risk of collision, we can go from this to a network that describes, that visualizes the interactions between these objects. And then from this network, we can actually extract useful informations, useful properties, to create a way to quantify the risk of collisions, to and then going to describe how this risk, how the sustainability of the population evolves in time. So there is so this is an application of networks that uses networks as a say as an instrument, as a midpoint to both represent what happens in space and to actually use, to actually compute something, to actually compute a measure of risk and a measure of how dangerous an object is, how dangerous is the situation in orbit in general. So this was all, and I hope I have been clear enough. I hope you managed to follow, and I hope you have been interested by this work. So thank you for your attention.
Thank you very much, Matteo. Very, very interesting. I see a little bit of TDA, topological with the sensor distance there.
Yes.
Very nice.
Yes, actually, you gave me the idea.
That's very good. That's very good. So actually, the student also have started seeing TDA. So you see, a topological data analysis, or as they say, análise topológica dos dados in Portuguese. So any question? Any question there? Let's see. No, we even have an astronomer. Fred, no question? An astronomer there. They have to absorb.
I'm going to show this, so it is recorded, and I'm going to show the slides anyway.
Yes. Okay, so thank you very much. I think that in September, I hope you're there. We have more to talk about this. I'm curious about the way how the TDA would work. If this will help to move the satellite before will increase. Will be something more than what you've done, or just find this something.
Well, it's nice to see. What I would like to do is to say, as I did before, to find, let's say, a meaning to this one, because actually I didn't include that. Just by simply studying, for example, the number of components, the size of the components, as you increase one or the other parameter, to maybe find a sweet spot for representation, even just for representation, because you have seen the picture. Wait, you have seen this picture here. I will share again. You've seen these pictures here. They are a mess. So it's difficult to represent anything with this one. Now I am using MATLAB to plot the networks, simply because it has a very good library. I will try other programs, but maybe by simply do some topological analysis.
They use Python library, but I guess it's comparable. It's the same. And
yeah, the thing is that I'm not so familiar with Python to work, say, fluently in it, but
but okay, in case we have some we have people that can help.
Yeah.
Okay. No, great. I see. Very good. Excellent.
Yeah, I hope your students
Yeah.
see that there are ways to use all of this for well, there are many ways to use all of this that they're studying. Just this is one of them.
Actually, some of them are applied and some are mathematical engineer. So it's very relevant for both. Thank you to you. So see you in September.
Yeah.
And
thank you. Yeah. Thank you again for
crossing fingers, see you in September. Okay. And thank you also to Matteo. And I'll stay on with just to say a few words. 1 second. I have a
yeah, there
question.
is I see now the chat. Sorry.
Yes.
Do you have any resource for application in astronomy? Oh, well, in astronomy or in
well, he say if you have some material.
well, I'm mostly focused on so artificial objects, so satellite and space debris. So astronomy, as in say astrophysics, not much, but this one I will write down the
Yes.
title and author. This is a very useful book. Actually, between this one and another one that I don't have here now, they have most of the information you need for about dynamics, for example. So the problem, risk analysis, and the dynamics of the space environment around the Earth. So equations of motions and so on.
Yeah, because Fred is from astronomy, so this is why. Yeah, so if you can send some information.
Yeah, I think, okay, for example, there are, speaking, say, more related to astronomy, to asteroids, I have seen networks applied to describe families of asteroids, also to identify, for example, well, not only, for example, the asteroids that come close to the Earth, where they have formed, so to which family they belong. I think that could be an interesting application for, say, more pure astronomy. What is the stability of exoplanets? I know someone who might. I know someone who work on that. So.
Yeah.
I will ask her
Okay.
if I can give the contact.
Okay, great. So it's already some connection. Okay. So thank you very much. Let's stop recording here.